folks, see you speaking again. In order for us to discover new things about the basic gates, we're going to start today with a summary. Let's do it. Now, we have here inputs. There are two typical inputs. We name them A, respectively B. So then, in order to compare all the functions, all the logical functions, to see what they do, the inputs, they have to take these values, exactly the same values for all the functions, both 0, or 0 and 1, or 1 and 0, or both of them 1. So this is the main rule for the inputs in order to get the functions. And now I'm going to get here all kinds of functions. A bar, B bar, A times B with the bar, A bar times B bar, A plus B with the bar, A bar plus B bar, A B bar times B, A B bar plus A bar B, A B plus A bar B bar. So now let's find out what these functions are. A bar right here and B bar over here. These are inverters, as you know very well. A times B. This is the AND. A times B with the bar in the top. This is the NAND. I'm going to pass over this one here. I'm using it as an intermediary calculation. A plus B is an OR. A plus B with the bar in the top is an OR. I'm going to pass over this one as an intermediary calculation as well as the next two ones. But we are going to calculate them. So let's find out. Much later, we're going to discover that this one here is going to be the XOR, and the last one here is going to be the XNOR. But with these things in mind, now we're going to write some values. A bar is the opposite of A. So if you know A, you're going to get A bar. So that's how we start to fill the values in the table. B bar, if you know B, the B bar is right opposite to it. So you're going to get this. So far so good. A times B. As you know very well, the AND, if at least one of the inputs is a 0, the result is a 0. So then you're going to get this. Only when both inputs are 1, only then the output is a 1. What is A times B with the bar in the top? Is right the opposite of the AND, because it's the NAND. So you don't need to calculate, you just put the opposite values, like this. Then you do A bar times B bar. So you have here A bar, respectively B bar, and you're going to get a 1, and then you're going to get zeros everywhere. And then you have A plus B. What is A plus B? Is an OR. So, OR is going to be like this. Remember the big trouble, 1 plus 1 is a 1, okay? A plus B with the bar in the top, this is the NOR. You don't have to calculate, it's right the opposite. So it's right the opposite of the one before. A bar plus B bar is going to be exactly this, like that. A times B bar. You take the A from here, and you take the B bar from here, okay? And then when you do the multiplication, you're going to get this. 0, 0, 1, and 0. Similarly, when you do A bar times B, is A bar times B, it doesn't matter the order, okay? You're going to get 0, 1, 0, and 0. The next one is what? Even if we don't know how does it work, you just add the previous two columns. So you're going to get 0, 1, 1, and 0. And the last one is going to do just the opposite of that, and you're going to get this. So this is a big table containing all kinds of values for outputs. It doesn't matter if we know all the functions or we don't. Now, what's interesting from this table though, let me highlight this by changing the color. If I'm doing that, let's notice something very interesting, okay? If you take a look here, and you take a look here, what can you notice? Is that these two columns, they have the same numerical values from the top, 1000, 1000. So these ones are actually doing the same result. What is the meaning of that? The meaning of that is what is in the head of the column, the expression, the mathematical expression here, are equivalent. And I'm going to write this thing right here in the top, okay? So it's going to be right here. A plus B with a big bar in the top is the same as A bar times B bar. And we're going to notice another interesting thing. This column here and this one here, they are also doing in similar way. 1110, 1110. What is the meaning? The meaning is that the head of the column right here and the head of the column of the other one, they are equivalent. I'm writing it down. A times B with the bar in the top is equivalent to A bar plus B bar. Now what happens is, remember who played first time with these kind of very strange letters with bars in the top? George Boole. And at least because of the what we know today as being the logic addition, 1 plus 1 is a 1. He didn't have too many friends, okay? Because it's not easy to convince someone about that mathematical calculation. But these ones, exactly these ones, were noticed inside the table by one of his very rare friends. Imagine, George Boole, for that reason, didn't have too many friends. So this was Augustus or Gus De Morgan. And the two relationships over here are known as being the De Morgan laws. So again, how these laws appeared? They appeared just because of some calculation right here in the table, and these are the relationships which are called today the De Morgan laws. And now, let me give you the reasons why I was drawing this big table for you, with all functions, all the basic functions, because here in that table you contain all the logic, the basic logic functions, building everything else in logic circuits. One reason is, if you have any gate, let's pick up the OR gate over here, and you have any package, and let's say the two inputs are 0, respectively 1, you know right away when you go for the OR gate over here, what the output should be, is a 1. So for that reason, when you do measurements, then you know exactly what to expect because you have all the basic logic functions in one table. You only have that, you only need that piece of paper with you. And by the way, because you know the logic functions here, let's attach some packages to them. Inverters, 7404, 7414. Let's put some CMOS ones, 4049, 4584, and the list goes on, okay? And very easy for the AND, 7408, and we can do 4081. So the list goes on. NAND, 7400, 4011, 74132, and so on. The list is big. Now OR, for the OR you have 7432, where you can have 4071. For the NOR you have 7402, you can have 4001, And then exclusive OR, if we don't know yet what it is about, you get 7486 and 4070. And for the XNOR, you're going to only find one, 4077. Okay? So when you pick up all these packages, and with these packages you start doing measurements, you know exactly what to expect inputs to outputs. A second reason I give you this big table is because of the De Morgan laws. The De Morgan laws, you are going to see that soon. They are the basics to simplify all the complex diagrams, and they are included in all the software regulating today software design. Okay? Because there is a lot of software design which is done by the computers instead of humans. Okay? And you have everything in that table. So far so good. So in the next video, we're going to discern, we're going to analyze, we're going to use the De Morgan laws in order to see how they work. So thank you very much for this one. See you for the next. Bye-bye.